Assalamualaikum and good morning. So today we would like to discuss the continuation of our lecture. So we are going to discuss about chapter 5, the stability of laminar flow. So in previous lecture, we already discussed that if we have a boundary layer, for example, we have a flat plate here. So the laminar boundary layer will occur, and then the transition, and then the turbulent boundary layer will occur. So in this chapter, we will focus on how to determine the transition region, which we call it as the stability of laminar flow. Because if the laminar flow is not stable, so means that it has tendency to become a turbulent boundary layer. So first, I would like to describe about the stability. Stability means a physical state which could withstand a disturbance and still return to its original state. So this is the idea of stability, means that it could receive an extra forces or the external forces, but that external force will not change the current situation. So the simple idea of the stability is showing like this one, as shown in your textbook, figure 5.1. If we have a few shape, we have A, B, C, and D. So we found that for figure A here, it can be classified as a stable situation, because if we give this ball an external force, so it will move like this, but at the end it will remain to its original position. So compare with B here, so means that if we push it even with a small amount of force, so this ball will move to another point. So for C, we call it as a neutral stability, because if we push it a little bit, means we apply an external force on the ball here. So this ball will move to another point, and then it will stop at that point. So means it is a neutral stability. So however, for this one, so maybe we could say it is stable for small disturbance, but unstable for large one. So means that if we just push with a small amount of force, so it will remain on its original position. But if we push with a huge amount of force, so this ball bearing will jump and move to another point. So means that the idea of stable means it could stay in its original position, original phenomenon, even though they are external forces act on the object. So, however, in fluid mechanics, we don't have a solid body like this one. So, the idea of stability means the changes of laminar to turbulent, because you know in turbulent there are chaotic movement. The molecule will flow, overlap, the streamline will overlap each other. They will have uh, chaotic and rule. It's not easy to predict the movement of the molecule in turbulent. So normally in fluid mechanics, we could check the laminar or turbulent by having or by calculating the Reynolds number. So however it is depend to the application, means the numbers, the transition numbers of Reynolds number is depend on the application. For example, for the flow in pipe here, normally if the Reynolds number is less than 2000, so we could say it is fully laminar. And if the Reynolds number is larger than 4000, we can call it as a fully turbulent. So if Reynolds number between 2000 and 4000, so means that the situation is in transition. So transition means that the flow cannot change to turbulent drastically. So it needs to change a little bit. Okay, so it changed gradually. So you could see that if, okay, so if for example we have a see-through pipe like this one, so and then we put a needle, means we put a small amount of ink continuously. So if the flow is laminar, we could find that the ink here is flow in a straight line, and we could see the ink. Why we could see the ink? Because the amount of ink is stay at one point, so we could see all the colors of that ink, of the dye. So and then after that, when if the pipe here is long enough, so after certain length, after certain time, so we found that the dye here is start to move chaotic like this, and suddenly we found that the ink will be disappear. So when the dye here flow fluctuate like this one, so this may be the transition region, means the flow is going into turbulent flow. So and then if the ink here is invisible, cannot be seen by our naked eye, so means that it is fully turbulent. So the idea is simple, because the dye particle is very small, and the turbulent means it chaotic, it's stir the dye molecule around, it stir the dye molecule in the flow, so now we cannot see the color of the ink. So that is the idea. So and this experiment is actually introduced by Reynolds. So the calculation of this one will produce a Reynolds number. Normally it is rho Vd over mu. This is the laminar and turbulent flow on flat surface. So this is the ideally sketch. So the idea here is, if the flow is laminar, so mean usually it is difficult for us to see any pattern of the flow. So for example, if we flow water on a flat surface, normally for laminar flow, so we found that the water will crystal clear, and it seems that it is a see-through of water flow here. But if the water start to flow in turbulent, normally we could see some kind of wave and so on. And then when it's flow in turbulent flow, so normally we could see some kind of a little bit a white mark on the flow, because the existence of wave. So you could see that if the wave in a seashore, you could find that it has a bubble a little bit, so the color is white. So means that the idea is, if the flow is turbulent, normally we could see some kind of flow pattern, a wave on the flow. Okay, however, now in chapter 5, we are focusing about the transition, because normally in our graduate, we are focusing whether it is 100% laminar or 100% turbulent. But in research level, sometimes we are focusing on the transition length. So and then for this one, we are focusing on flow on bluff body. So mean flow on a plate, so instead of flow inside a pipe, because in flow inside a pipe, so the transition length normally can be ignored, because it is normally occur at the starting point of pipe. That's why if you read about the flow in pipe, so we have the fully developed region. So fully developed region means the flow is fully developed, so mean normally it stay in turbulent. So means that the region between, if you have a tank here connected with a pipe, so normally at certain distance at the inlet here, so it may be undeveloped flow, and then after the boundary layer and the velocity is stable, so the fully developed region started. So normally in flow in pipe, we don't have any problem in terms of transition. So if we see the Reynolds number for flow in pipe, so the limit is between 2000 and 4000. So it is very small and normally it's not be an issue for in research. So but flow on a plate like this, whether it is a flat plate or a curved plate, okay, so normally transition sometimes need to be more attention. So normally for the aerospace research, because at certain speed we start we have the laminar boundary layer, and after that the transition comes in, and then the turbulent boundary layer comes in. So normally because the transition or the limit, which is the 5 times 10 to the power of 5, is quite big. So mean the transition of this one need to be a serious attention. So in chapter 5 here, so we will discuss about how to determine the instability, or how to determine the location or the Reynolds number where the transition between laminar and turbulent will be occurred. So this is actually the idea, the picture taken from the textbook. So you could see that if we see some kind of pattern here, so it means that the flow start to become a turbulent flow. Okay, in this chapter, if you read the textbook, they will give you a lot of explanation about the idea of stability. However, because we are not going to read page by page, so I just summarize the equation, because I think uh, it is okay for us just to know the equation and we know to solve the problem, because the theory after that, if you see the tutorial, you will find that actually the theory about how to determine the transition is different. It is we have a few theory to be used. Okay, it's not fixed with one equation. So means that we could try a few equation and the answer is sometimes is slightly different. Okay, that's why in this lecture I would like to just share you a few equation that be used to determine the transition, and then we could learn from the tutorial. So this is a note. I list the Fagner-Scan solution. So the idea of Fagner-Scan solution is the calculation, the basic calculation of boundary layer if the object is not parallel with the free stream velocity. So the idea is the Blasius is written assume like this one. However, for the Fagner-Scan, so it gives us the extra of m plus 1 here. Which beta here is equal to 2m over m plus 1. And then the Blasius momentum thickness can be calculated like this one. And however, the Fagner-Scan, so we have this equation. So don't worry. So I will explain details in tutorial. So this is just the equation, the overall equation that we will use in our tutorial. So this is a Fagner-Scan solution, and previously I give you the equation of the Twitch solution. So normally in this case we are focusing on Cartesian coordinate, because we are focusing on flow on aerofoil or flow on flat surface. So we are not using the polar coordinates for the calculation of nozzle, for example, or the calculation of separation or the transition inside the pipe. So it is okay for you just to remember this equation. So in final exam, especially, maybe I will list all the equation and also the important parameter, the appendix. So I hope you could use that appendix when you answer that question. So and then we will have another equation, which is Michel solution. So this is the equation. So later on I will show you the how to use this one. So we have a Wazan solution, we have the Venn Dryas and Blummer solution, and we have a Dunham solution. So certain solution, for example, the Venn Dryas and Dunham solution sometimes used when we have a turbulent portion or a turbulent percentage in our free stream velocity.